In this lecture, we're going to discuss electromotive force, current, resistance, potential difference, and basically talk about Ohm's law. We have a picture of two kinds of batteries here, and you'll notice that there's a battery symbol. The long line, the longer line here is a positive, and the shorter line is a negative. And what happens here is this battery sets up an electric field in the circuit and pushes charges through the circuit in order for those charges to do work. And because of the positive and negative charges on the battery terminals, an electric potential difference exists between them. The maximum potential difference is called the electromotive force, the EMF, of the battery, for which the symbol E is used. You'll also see it interchanged with capital V, potential difference, but you'll also see this term electromotive force. In a typical car battery, the chemical reaction maintains the potential of the positive terminal at a maximum of 12 volts. 12 joules per coulomb is what that means. It's higher than the potential of the negative terminal, so the EMF is 12 volts. What happens here is that's basically the pressure that's put on the charges to move through the circuit. If it was a 9-volt battery, those charges coming out would have 9 joules of energy per coulomb of charge that came out. A 12-volt battery has 12 joules of energy per coulomb of charge. It just pushes it. The 12-volt battery basically just has more pressure pushing those charges out of that battery. They have more energy coming out, so they can do more work. So this bottom paragraph says, thus 1 coulomb of charge emerging from the battery and entering a circuit has at most 12 joules of energy. This potential difference causes electrons to move from the area of low potential to an area of high potential. They want to go to the positive area. In other words, a current flows through the circuit and does work. The electric current is the amount of charge per unit of time that passes through a surface that is perpendicular to the motion of the charges. The electric current is defined as the amount of charge that passes through the circuit each second. So the equation is I, which is current, equals delta Q. That's the amount of charge per delta T seconds. So if we look at this, we have the current from the 3-volt battery pack of a pocket calculator is 0.17 amps. In 1 hour of operation, how much charge flows in the circuit, and how much energy does the battery deliver to the calculator circuit? And what we're going to do is use our equations. So we're going to write our equation down here. We're going to use the equation I equals Q over T. And we want to solve for Q. So we want to solve for how much charge flows in the circuit. So Q equals I times T. And so I'll put in my current of 0.17 milliamps, which is 0.17 times 10 to the negative 3 amps. And my time, I'm going to multiply that by, and I have to have it in seconds, not hours. So we have, there's 3,600 seconds in an hour. We go ahead and multiply that out, and we end up with an answer of 0.61 coulombs. Now part B wants us to solve for how much energy does the battery deliver to the calculator circuit. So we want to solve for energy. We want to know how much work is going to be done or how much energy. And you'll typically see it as work equals, and that's what we want to solve for, is the energy. And what we need to realize is that 3 volts is really the potential difference. Now 3 volts can be thought of as 3 joules per coulomb. So what I really need to do is multiply by 0.61 coulombs, and those coulombs cancel, and I'm left with joules. So I have my answer of 1.8 joules. Now this leads to the idea of an equation: work equals Q times delta V. So we know that volts is a joule per coulomb, Q is coulombs, so it leaves us with joules. So here's a new equation we came up with just now on solving this problem. So now we actually have two equations we're working with. Now the textbook uses conventional current to describe current flow. This is not following electron flow, but positive charge flow. Conventional current is acting as if positive charges flow, even though it's really electron flow. Um, since Ben Franklin picked the wrong charge, Ben Franklin said that electricity was the flow of positive charge. It has stuck over the years and historically has stayed that way. In college, you'll see conventional current used instead of regular current. So in a circuit, we'll have to measure and calculate three things. Current, which is I, that's measured in amperes or amps and has the letter A for its units. Potential difference equals capital V, which is volts, and the units are small v, actually. Resistance is capital R, it's measured in ohms, and the units are an omega symbol. And resistance is similar to friction. So what this comes down to is potential difference is basically the pressure pushing the charges out of the power supply, out of the battery. The current is how much charge is flowing per unit of time, so it's how many coulombs of charge per second. And then the resistance is how much are the wires and the resistors and so on stopping that flow from happening. And the equation that shows these properties is called Ohm's law. R equals V over I. So here's a circuit where we have our power supply. You see the 36 volts comes up through here, goes through this resistor, which we can see as 36 volts as well. Comes down here the current, and you'll see it's 360 milliamps of current, and comes back through, so we have a complete circuit. Now if I increase that resistance, we'll see that the current goes down. Potential difference doesn't change though, because the potential difference is going to stay the same the whole time. The power, but as soon as I start changing the power or the voltage, you can see that the current will change as well. So if I increase the voltage, you can see that current's going up, but you'll see that this potential difference across the resistor matches this power supply. So we're going to look at the graph of Ohm's law. Now you have this relationship. Ohm's law says resistance equals potential difference over current. Now what we're going to do is we're going to graph potential difference on the y-axis. We're going to graph current on the x-axis. And what you see up here, if you look at a straight line, let's say we graph the current in a circuit, what you're going to get is this. You're going to get some kind of you'll get some kind of graph that looks like this, because what we have here is that the voltage over current equals resistance. And you'll see, since this is the voltage is on the y-axis, current is on the x-axis, you really have change in y over change of x, which is really the slope. So the slope of this line equals the resistance in the circuit. And so you'll see that this resistance is not quite as big as this particular resistance. So you draw here, you draw another circuit, and you'll have a bigger resistor in that circuit because the slope is larger. You'll see voltage here, and you come across and you'll find the current, so you'll have a high voltage will be a higher current, low voltage will be a lower current, and that follows this relationship of Ohm's law here. R equals V over I. And that's how the graph works. The slope equals the resistance. So we'll look at this particular problem here. We say that the filament in a light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current in it. Figure 20.7 shows a flashlight that uses two 1.5 volt batteries, effectively a single 3 volt battery, to provide a current of 0.4 amps in the filament. Determine the resistance of the glowing filament. So what we'll do is we'll use the equation, Ohm's law. And so we'll write that equation down right here. R equals V over I. And we'll go ahead and plug in our values. We have 3 volts. And you get 0.4 amps. So that then gives us a resistance of 7.5, and the units there are ohms. So the three equations we've learned here today are I, current, equals Q, charge, over time, T. We also learned that the energy in the circuit can be calculated by the amount of charge going through the circuit with a certain potential difference pushing it through the circuit. And we also learned Ohm's law, that the resistance is equal to the potential difference across the resistor, the potential drop across the resistor, divided by the current.